Besides those principles we learned of relative dating, fossils are another important indicator of time in geologic records. Fossils are traces or remains of prehistoric life preserved in rock, and paleontology is the field of science studies fossils. It is an interdisciplinary science which actually combines biology and geology. Knowing the nature of life that existed at a particular time helps researchers understand past environmental conditions. Usually, such materials like teeth, bone, and other hard materials coming out from living organisms are easier to preserve in forms of fossils. But we also see some more delicate material preserved in geologic layers. Depending on different environments or different ways that they form, we actually can group fossils under different names. So permineralization is one type of procedure which actually creates fossils. In this case, we have mineral-rich groundwater, and this groundwater flows through the porous tissue of material, any kind of living organism, and then the minerals will precipitate in those porous media, and then it will form a fossil. Most common example for this kind of fossil is actually petrified wood. We also have molds and casts. A mold is going to be created when a shell of, for example, a sea creature is buried. This material is actually calcium carbonate, and it is going to be easily dissolved by the underground water. So this hollow space created or left after the shell was dissolved will be called as mold. And when we have this mineral-rich groundwater actually carrying more material into this hollow space and fill it with the precipitated minerals, we will have casts, which is another type of fossil. There is also carbonization and impressions. Carbonization happens when an organism is buried underneath some fine materials in such as a very quite sedimentary environment like those wetlands, for example. These layers of fine material will be pressured underneath the layers coming after them. And this pressure will lead to those layers losing their gases and liquids and having them being compacted. In this case, the remnants of any kind of organism will be preserved as a thin carbon film. And one later stage of this kind of fossil forming will be impressions. When this carbon film is lost, the remaining will be impressions in those fine grained materials. So here in this picture, we actually have two examples of a fossil bee preserved as a thin carbon film, and also a fish showing all of the structures of the fish in considerable detail as an impression. Another type of fossil forming will be amber. Amber is actually the hardened resin of ancient trees. It actually is effective in most of the cases preserving real delicate insects. So the insect gets trapped in this resin coming from an ancient tree, and this resin itself is actually serve as both something against the pressure, so it actually will save the insect from being crushed, and it also is going to save the delicate features of that insect. There are also trace fossils. In this case, they will be the indirect evidence of the prehistoric life. They can be coming from tracks or burrows, like the holes that worms dig in the soils, and also they can be coprolites or gastrolites. So these actually are the materials such as dung or the stones and the kidneys of some sort of reptiles, which are actually extinct right now, but they use those real nice polished rocks to help with their digestive system. And you see in these pictures examples of this kind of fossil forming. Here we have a spider in amber, and then here we have a coprolite, which is a fossil dung. And for fossil forming, there are several conditions which are actually favoring preservation. First of all, we need to accept that most organisms are not preserved. In many cases, we will have bones, fragments and shells are being easier to preserve than some delicate material and flesh and insects. In these cases, actually, the fossil forming will be more successful if we have rapid burial of the material, and also if there is hard parts of the organisms. So in both of these cases, when we have rapid burial and the hard parts of the organisms, the chances of preservation is going to be better. We also can correlate rock layers by using the principles we learned before. So by just looking at these different layers in their orders, we can identify if they are following each other. So here you see actually a long transect in between three national parks. And we actually can correlate all these layers, sedimentary layers, from each of these different regions. In most of the cases, correlation actually provides a more comprehensive view of the rock record. So beyond being locally correlating those rocks, we actually can correlate the material in long distances. And correlation with limited areas are going to be quite easy by using the relative dating principles. Often we just can accomplish this by noting the position of the bed in a sequence of strata, and by following which layer is coming after which other layer, we can correlate those materials being close to each other. And we can match these different rocks from similar ages in different regions. However, when we need to correlate over larger areas, we will need the aid of fossils for helping us to create these sort of correlations. So there are several principles that we can use for going after this larger areas correlation of layers. The first one is the principle of fossil succession. So we know that in actually the Earth's history, we have different eras, different types of the organisms, which will provide us different types of fossils being grouped. And in this case, we can actually have them arranged according to their age. So for example, we know that the age of trilobites was the oldest one. And after that, age of fishes followed, and then age of reptiles and age of mammals came last. So by looking at the existence of these different types of fossils, we can understand, or we can put those layers, different geological layers, into a time context. There are also index fossils and fossil assemblages. Index fossils are widespread geographically and limited to a short period of geologic time. Here in the picture, you actually see those index fossils under microscopes. These teeny tiny shell craters are staying together, and by looking at their combination, their organizations, we can use them for timing different layers. And by looking at these two together, we can extend our capabilities of correlating rock layers for real long distances. Here we see a foil assemblage, which is a group of fossils used to determine a rock's age. So here at the bottom, let's say we have a rock unit B, and we have some trilobites, some seashells all together. And when we go away to some other area carrying more or less the same kind of geologic layer, we can just follow this unit. And if we see the same kind of combination of the fossils in that unit, we actually can correlate that further away unit B with this unit B in here. Or same thing can happen in here. So by looking at the age ranges of these fossil groups and their existence being grouped together, we can correlate different layers from different areas and put them in the same time scale. We also can use fossils as environmental indicators. By looking at for example, shelf thicknesses, we can understand the existence of ancient shorelines or seawater temperatures. By looking at different materials in those shells of the sea creatures or organisms, we also can identify the climate properties in that time and for that environment. So fossils both can be useful for identifying different times or helping us to correlate different layers from different regions or put them into the same time frame together. So in the next lecture, we will talk about this geologic time scale a little further, and we also will learn about radiologic dating.